Hello, Honors Physics students. I want to talk about one of the homework problems, specifically number 30 here from the textbook. So I just want to pull that up in front of you, have yourself familiarized with it. I'm seeing a lot of good work, but I'm also starting to see some things that are not quite right, and you're getting the right answer, but you're sort of fooling yourself into how you're getting it and what you're doing with this. You may recall when we had done another problem involving conservation of energy, specifically the rocket that was launched straight up. We had done conservation of energy, and we canceled out the mass, and we got to this equation, V naught squared equals Vf squared plus 2gHf, and while we were doing it, I said, hey, what does that sort of look like? And a lot of you said, well, it looks a little bit like the time-independent kinemax equation. And if we leave it even more general, let's say the initial potential energy wasn't zero, in which case there would still be this 2gh naught term, thinking through how we multiply everything by 2, right? And if we rearrange that for Vf squared as V naught squared plus 2g h naught minus hf, that is starting to look even more like the time-independent kinemax equation. Here they are, top bottom, so you can really see them, and you can see the similarities, that they're very, very similar to each other. And for the problem with the rocket was going straight up and down, well, they are essentially equivalent to each other. But there's some issues as you try to apply this maybe to a problem like number 30. See, Vf squared equals V naught squared plus 2a delta y is the time-independent kinemax equation. It is a one-dimensional kinemax equation, and really it's only for 1D motion, an object moving in a straight line, either straight up and down, or straight forward and back, or straight left and right, or even moving along an incline. An incline is straight line motion. You can certainly use this. It wouldn't be delta y, because that would be a change in vertical position, maybe more Vf squared equals V naught squared plus 2a delta x, but delta x could be the length of the incline. That's absolutely fine. But then you look at problem 30, and this is obviously not one-dimensional motion. There's no straight lines here at all. The track is always curved, and so it's completely wrong to try to use Vf squared equals V naught squared plus 2a delta y in this case, even though there are changes in heights. There's another really important reason why we can't do this. In the equation for time-independent kinematics, we have the acceleration, and some students are using the acceleration as g and getting a right answer, because of course if you just look up one line from that, g plays the role of a. But the problem is, if you look at problem 30, there is no way the acceleration is g, right? The acceleration being g means the object is in free fall, and there's no way this bead is in free fall. It's on a track. It's supported by the normal force. There's no way that the only force is the force of gravity. And so we can see from all perspectives that using the time-independent kinemax equation is completely wrong. The problem is, as I said before, you can fool yourself into thinking you're doing it correctly, because if you put in the change in vertical position along this curved track and you say the acceleration is g, you are going to get answers that are correct, because you can clearly see that would just be one line up from our derivation here, Vf squared equals V naught squared plus 2g h naught minus hf. You're going to get the right stuff. And so you fooled yourself into thinking you have a correct solution. What's the workaround? How do we do this? Well, here's what you do. In a situation like this, where it's clearly not going in one-dimensional motion, and the acceleration is clearly not g, we start with conservation of energy, or the equation with the WNC term in it. The point is, you start from a work and energy approach, and then you cancel mass out, and you do the algebra, and then you might get to an equation that looks an awful lot like this one, Vf squared equals V naught squared plus 2g h naught minus hf, or some version of that, and only then can you put numbers in. But what you absolutely shouldn't do is start with the time-independent kinemax equation. And I'm just warning you now that if you do that, for example, on a test or a quiz, well, you're not going to get credit for it, because even if you do happen to get the right answer, you're not really understanding what's happening. You are thinking the object's moving in a straight line. You are thinking the acceleration is g by putting in 9.8 for the acceleration, by putting in delta y as delta h or delta x, whatever it is. And like I said, you're sort of fooling yourself into getting a right answer when you're really not justified in doing so. And there are plenty of other situations that we've seen in your homework problems that fit the bill, where you really shouldn't be using the time-independent kinemax equation, but maybe you did. And so I want you all to go through your homework and see if you are erroneously using the time-independent kinemax equation, and please go back and fix it. You should really change your solution to start from an energy approach, and then do the algebra, and then get to the equation that sort of looks like it, and only then should you be putting the numbers in. And so before next class, I want you to see if you can find as many different situations that fit the bill here, where we really shouldn't be using the time-independent kinemax equation, and yet if you do, you're going to get an answer that looks correct. And then next class we will go through as many different situations as we can in the homework problems, so we can identify where this may happen.